When we imagine life beyond Earth, we almost always picture a planet, a solid surface, an atmosphere, oceans resting in basins carved by gravity, a star rising and setting across a sky. These images feel so natural that we rarely question them. In our minds, life and planets are inseparable. No ground, no oceans, no world to stand on, then surely no life. But that assumption may say more about our own origins than about the universe itself. If we pull back far enough, something strange becomes clear. Planets are not the dominant feature of the cosmos. They are rare islands embedded in an ocean of emptiness. Most of the universe is not made of world surfaces or stable ground. It is made of diffuse gas, drifting dust magnetic fields, radiation and energy flowing through near vacuum. Between the stars lies an environment that dwarfs every planetary surface combined, and yet we almost never ask whether life could exist there. Instead, we treat planets as a requirement. But are they? From a physical perspective, a planet is not life itself. It is a container, a structure that provides stability, chemistry, protection, and time. It gathers matter, holds onto heat, and shields delicate molecules from radiation. Planets do not create life. They merely make certain conditions easier to maintain. And once that distinction is made, a deeper question emerges. If life is not defined by soil, oceans, or continents, but by processes, by the ability to extract energy, maintain structure, store information, and adapt, then perhaps planets are only one possible solution, not a rule, not a universal necessity. Just one way the universe happened to package those conditions in our corner of space. To understand whether life could exist without planets, we must first loosen our definition of what life actually requires, not philosophically but physically. At its core, life is a system that stays far from equilibrium. It feeds on energy gradients. It resists decay. It copies patterns with variation. None of these processes in principle demand a solid surface beneath them. They demand chemistry, energy, and persistence, but not necessarily a world. The universe is filled with environments that offer energy without ground, chemical complexity without continents, stability without gravity, wells large enough to be called planets. There are thick atmospheres with no surface beneath them, vast molecular clouds where organic compounds assemble on dust grains in the dark, oceans locked beneath kilometers of ice drifting free from any star, even regions of space where radiation and magnetic fields form long-lived structures that behave less like chaos and more like organized systems. These environments are not friendly by Earth standards. But Earth standards are not universal standards. For most of cosmic history, planets did not exist at all. The early universe was a sea of gas and radiation threaded with simple atoms and expanding relentlessly. And yet even in that primordial darkness, chemistry began to organize itself. Complexity appeared long before solid worlds did. That alone should give us pause. If chemistry can self-organize without planets, then the boundary between habitable and lifeless may not sit where we think it does. The real challenge is not imagining exotic creatures floating through space. It is understanding whether any environment can provide three critical ingredients for life to persist: a sustained source of usable energy, a medium where complex chemistry can operate, and enough stability for information to accumulate over time. Planets happen to provide all three, but they are not the only structures capable of doing so. And once we accept that possibility, the search for life changes direction. Instead of asking where planets like Earth might exist, we begin asking where the universe accidentally creates pockets of order, places where matter lingers, gradients endure, and chemistry is given time to experiment. Some of those places may look nothing like worlds. Some may never form continents, oceans, or skies. Some may never know a sunrise, yet they may still be alive. In this journey, we will step away from surfaces and horizons. We will leave behind the comfort of planets and follow life into environments that feel hostile, empty, or impossible at first glance. We will ask whether atmospheres alone can host living systems, whether oceans need a planet beneath them, whether clouds, ice, dust, and darkness can become homes rather than obstacles. And by the end, the question may no longer be whether life needs planets. It may be whether planets were ever the most likely place for life to begin at all. Before we can decide whether life can exist without planets, we need to do something deceptively difficult. We need to strip the idea of life down to its functional core, separating what is essential from what is merely familiar. On Earth, planets do many things at once. They provide a surface where matter can collect. They trap heat. They hold atmospheres. They recycle chemicals through geology, weather, and oceans. Because all known life exists on a planet, it is easy to assume that life requires all of these features together. But from the perspective of physics and chemistry, a planet is not a requirement, it is a convenience. At its most basic level, life is a system that uses energy to maintain structure against decay. It does not have to walk, breathe, or grow roots. It must only do three things reliably. It must access a persistent energy source. It must operate within a chemical or physical medium capable of forming complex patterns. And it must preserve information long enough for selection and adaptation to matter. Everything else is negotiable. A planet helps by bundling these conditions into a single package. Gravity pulls material together, creating density. A solid surface or deep ocean provides containment. An atmosphere moderates temperature and shields fragile molecules from radiation. Geological processes recycle elements and create chemical gradients. Over billions of years, this stability allows complexity to accumulate. But none of these functions are exclusive to planets. Energy, for example, does not originate from surfaces. It comes from gradients, differences in temperature, chemistry, radiation, or electric potential. On Earth, sunlight drives most life, but even here, entire ecosystems survive without it. Deep beneath the oceans, communities thrive around hydrothermal vents, powered entirely by chemical reactions. No light, no photosynthesis, just energy flowing through matter in the right way. That lesson generalizes. Wherever the universe maintains a long-lived gradient, energy is available. Radiation fields vary with distance and shielding. Chemical reactions release energy when incompatible compounds meet. Magnetic fields store and release energy through reconnection events. Even radioactive decay provides a slow, steady heat source over billions of years. None of these processes require a planet beneath them. The second requirement is a medium capable of complexity. Life as we know it uses liquid water because it is an excellent solvent. It allows molecules to move, collide, assemble, and rearrange. But water is not magical. It is simply effective. Other liquids, supercritical fluids, icy matrices, or even structured plasmas could in principle support complex interactions under the right conditions. What matters is not the substance itself, but its ability to host reactions that are neither frozen nor explosively chaotic. The medium must allow structure to form, persist, and change gradually. On Earth, oceans and cells provide that balance. Elsewhere, different environments may play the same role in unfamiliar ways. The third requirement is the most subtle and the most difficult to satisfy. Without planets, life must store information. It must remember what works. On Earth, this role is played by DNA and related molecules protected inside cells and organisms. Without containment, information dissolves. Molecules drift apart. Patterns blur into noise. This is where planets excel. They create enclosed spaces, pores in rock, ice-covered oceans, atmospheric layers with stable circulation. These act as natural compartments protecting information from rapid loss. Remove the planet and the challenge becomes clear. Space is dilute. Radiation is intense. Structures tend to disperse rather than concentrate. Any attempt at life without planets must overcome this tendency. It must find ways to create compartments, barriers, or repeating structures without relying on gravity-driven surfaces. Yet the universe already does this in other contexts. Dust grains gather icy mantles. Magnetic fields confine charged particles. Turbulence creates long-lived vortices. Chemical films self-assemble at interfaces. These are not organisms, but they demonstrate that containment and structure can emerge spontaneously under the right conditions. When we step back and look at these requirements together, a pattern emerges. Planets are not fundamental to life. They are one solution among many, a highly effective solution but not the only one allowed by physics. The real question is not whether life can exist without planets in principle. It is whether the universe provides alternative environments that satisfy these three conditions for long enough periods of time, long enough for chemistry to become organized, long enough for information to stabilize, long enough for selection to begin shaping complexity. To answer that, we need to examine specific environments where planets are absent, but energy, chemistry, and structure still persist. Not in theory, but in places that actually exist in the universe. The first of those environments may feel surprisingly familiar. Not solid ground, not oceans, but vast layered atmospheres, places where life might float rather than stand. And that is where the next part of our journey begins. When we think about atmospheres, we usually imagine them as thin skins stretched over solid worlds, a place to breathe, a buffer between a surface and space, something life lives beneath, not within. But that framing hides a deeper truth. An atmosphere is not empty air. It is a dynamic, layered environment filled with motion, chemistry, and energy. In the right conditions, it can behave less like a sky and more like an ocean. One with currents, gradients, suspended particles, and stable zones that persist for long periods of time. From a physical standpoint, there is nothing that says life must rest on a surface. It only needs a medium dense enough to support interactions and structured enough to prevent immediate dispersion. Thick atmospheres can provide both. Consider what an atmosphere actually contains. Gas molecules collide constantly, exchanging energy. Temperature varies with altitude, creating vertical gradients. Radiation from a nearby star or background sources drives photochemical reactions. Electrical activity such as lightning injects bursts of energy that can break and reform molecular bonds. And within this turbulent system, tiny particles dust. Aerosols droplets can remain suspended for years, even centuries. These suspended particles matter. They act as surfaces without ground. Platforms where chemistry can concentrate rather than disperse. On Earth, aerosols already host complex reactions. Organic molecules form and transform within cloud droplets. Chemical pathways emerge that do not occur at the surface. Life does not exploit these environments here, but the chemistry is already active. In a much thicker atmosphere, those microenvironments could become long-lived. Layers with stable temperatures and pressures could persist indefinitely, especially if convection cycles keep material circulating rather than allowing it to fall or escape. In such a system, up and down replace land and sea. Organisms or organized chemical systems could drift, sink, rise, and harvest energy simply by changing their density or structure. Energy in this context is abundant. Sunlight filters through atmospheric layers, changing in intensity and wavelength with altitude. Chemical gradients arise naturally as different gases mix imperfectly. Electric fields build up and discharge. Each of these gradients represents usable energy waiting to be tapped by any system capable of exploiting it. The greatest challenge is stability. Atmospheres are restless. Turbulence threatens to tear structures apart. Radiation can destroy complex molecules. Without a solid boundary, how does information persist? How does a system avoid being diluted into irrelevance? The answer lies in repetition and cycles. Atmospheric circulation is not random chaos. It forms predictable patterns, cells, bands, jets, and vortices that can persist for years or longer. Within these structures, material follows looping paths. A particle can experience the same sequence of conditions again and again. Warm to cold, light to dark, chemically rich to depleted. This repetition creates something essential for lifelike behavior, a rhythm. If chemistry can couple itself to that rhythm, information no longer needs a static container. It can be carried by motion itself. Patterns that survive the cycle persist. Patterns that fail dissolve. Selection becomes possible not through location but through behavior. Over time, systems could emerge that actively regulate their buoyancy chemistry or charge to remain within favorable layers. They would not walk or crawl. They would float, sink, and drift. Their metabolism would be the control of motion and reaction rates within a moving medium. From a distance, such a biosphere would leave subtle signatures, unexpected chemical imbalances, persistent concentrations of reactive molecules that should quickly disappear, layered spectral features that defy simple atmospheric models. And crucially, these systems would not require a planet with a surface. They would only require an atmosphere thick enough to act as a sea and stable enough to persist across geological timescales. This idea stretches intuition, but it does not break physics. It simply replaces ground with gradients and land with layers, and once we accept that air itself can become a habitat, the boundary between planetary and non-planetary life begins to blur, because the next environment we must consider takes that idea even further into places where there may be no surface at all, not even buried beneath layers of gas. Places where oceans exist without shores sealed beneath ice drifting through the darkness between stars. When we hear the word ocean, we instinctively imagine a planet beneath it, a rocky shell, continents, gravity holding water in place. But from a physical standpoint, an ocean is not defined by land. It is defined by phase, liquid confined by pressure, temperature and energy balance. And under the right conditions, liquid water does not need a planetary surface at all. In recent years, scientists have come to accept that oceans hidden beneath thick ice layers may be common throughout the universe. On moons and distant worlds, kilometers of ice can trap water below, shielding it from radiation and insulating it against the cold of space. Beneath that frozen lid, liquid persists dark, pressurized and stable over immense spans of time. But now remove the assumption that such an ocean must belong to a large planet. Imagine a massive ice-rich body drifting freely through interstellar space. No star, no surface exposed to sunlight. At first glance it seems lifeless, frozen solid, dead, yet deep inside a different story may unfold. Radioactive elements embedded within its interior slowly release heat. Chemical reactions between rock and water generate additional energy. Over time, this heat accumulates, melting pockets of ice and forming subsurface reservoirs of liquid water. These are oceans without shores. They do not experience day or night. They are not shaped by weather. They exist in permanent darkness, sealed beneath ice that acts as both armor and insulation. Within these hidden seas, conditions can remain remarkably stable. Temperatures fluctuate slowly. Radiation is nearly absent. Chemical gradients persist as water interacts with minerals below. From the perspective of life, this is not a hostile environment. It is a protected one. Energy does not arrive from sunlight but from chemistry. Reactions between water and certain minerals release hydrogen and other compounds capable of fueling metabolism-like processes. This is not speculation drawn from imagination. On Earth, entire ecosystems thrive around deep-sea hydrothermal vents powered by chemical energy alone. They are isolated from the surface, independent of photosynthesis, and astonishingly resilient. The key difference is scale. On a drifting ice body, the ocean may be smaller, fragmented into pockets rather than global seas, but it may also last longer. Without tidal disruptions, surface impacts or stellar radiation, such environments could remain undisturbed for billions of years. Time more than abundance may be the critical ingredient for life to emerge. The absence of a planetary surface introduces challenges. There is no large-scale circulation driven by winds or tides. Mixing occurs slowly. Nutrients may become localized. Evolution proceeds at a different pace. But slowness is not a flaw. In a universe measured in billions of years, slow systems have time to explore complexity. If life arises in such an ocean, it would never know a sky. It would never experience seasons or sunlight. Its evolutionary pressures would be shaped by chemistry pressure and the gradual rearrangement of its environment. Selection would favor stability, efficiency, and resilience rather than speed. From the outside, these worlds would be nearly invisible. They emit little light. They reflect almost nothing. They drift silently through the dark, indistinguishable from inert ice unless observed closely. And yet inside they may host one of the most stable habitats the universe can offer. This possibility forces a shift in perspective. Life may not require a planet in the traditional sense. It may only require a volume where liquid can persist, energy can flow, and chemistry can repeat itself long enough for information to take hold. If oceans can exist without shores, then habitability no longer maps neatly onto planets and stars. It spills outward into objects we would normally dismiss as debris, and that realization prepares us for the next step. Because if life can persist inside isolated oceans drifting through space, then we must ask an even more unsettling question. Could living systems survive not just without planets, but without stars at all? That question leads us to worlds that wander completely alone. When astronomers first began to discover rogue planets, worlds drifting through space without a star, they seemed like cosmic orphans. Cold, dark, ejected from their birth systems and condemned to wander forever. In the traditional picture of habitability, these objects ranked near the bottom. No sunlight, no seasons, no obvious energy source. And yet, from the perspective we are now building rogue planets, force an uncomfortable realization. They are planets in name, but not in function. What makes a planet habitable is not its orbit around a star. It's the ability to maintain internal conditions that support long-term chemical activities. And rogue planets, despite their isolation, may do this surprisingly well. Deep inside any sufficiently massive rocky body, radioactive elements decay, slowly releasing heat over billions of years. This is not a minor effect. On Earth, radiogenic heating drives plate tectonics volcanism, and the long-term cycling of carbon. Remove sunlight entirely and that internal heat remains. Reduce surface temperature to near absolute zero and the interior can still stay warm. Add a thick insulating layer ice rock or both and heat becomes trapped. In this way, a rogue planet can resemble the ice-covered ocean worlds we considered earlier, but on a much larger and more stable scale. Beneath kilometers of frozen crust, liquid water may persist indefinitely. Chemistry continues. Gradients remain. Time stretches forward uninterrupted. From the inside, such a world does not feel abandoned. It feels constant. There is no sunrise to miss, no nightfall to fear. The environment is defined not by celestial motion, but by equilibrium. For life, this kind of stability can be more valuable than energy abundance. Evolution does not require brightness. It requires persistence. The crucial insight here is that the star was never the essential ingredient. It was merely the most visible one. Stars provide energy quickly and dramatically, but they also introduce volatility. Flares, radiation, storms, and stellar evolution can destabilize environments. A rogue planet escapes all of that. Its isolation becomes a form of protection. But this also exposes a subtle shift in our reasoning. If a rogue planet can support life without a star, then the star is optional. And if the star is optional, then the planet itself begins to look less like a requirement and more like a convenient scaffold. The true function of the rogue planet is not to be a world. It is to be a container, a large long-lived compartment that prevents heat and chemistry from dissipating too quickly. In that sense, it is simply one of many possible structures capable of performing the same role, which leads us forward. If we strip away the size, the gravity, and the familiar shape of a planet, what remains? Smaller bodies also contain heat. Smaller bodies also trap chemicals. Smaller bodies also persist for long spans of time. And once we begin thinking in those terms, an unsettling possibility emerges. Perhaps life does not require worlds at all. Perhaps it can survive intermittently, adaptively, or cyclically inside objects we usually regard as too small, too cold, or too unstable to matter. Objects like comets, asteroids, and the countless fragments of ice and rock drifting silently between the stars. That is where our next investigation takes us. At first glance, comets and asteroids seem like the worst places to look for life. They are small, fragmented, exposed to radiation. Their gravity is weak. Their temperatures swing wildly, and many spend most of their existence frozen in darkness. In the traditional hierarchy of habitability, these objects barely register. They are treated as debris leftovers from planet formation, chemically interesting but biologically irrelevant. Yet that dismissal rests on a quiet assumption, that life must be continuous, active, and uninterrupted. The universe does not require that assumption to be true. Comets and asteroids are not chemically empty. On the contrary, they are among the richest reservoirs of organic material known. Complex carbon-based molecules form on their icy surfaces, and within their interiors assembled slowly by radiation, cosmic rays, and catalytic reactions on dust grains. Many of the building blocks associated with life on Earth, amino acids, nucleobases, simple sugars, have already been identified in such bodies. What these objects lack in size, they partially compensate for in number and longevity. Trillions of them drift through planetary systems and interstellar space. Some remain undisturbed for billions of years. Others experience periodic heating as they pass near stars or collide with larger bodies. These cycles matter. Even brief heat changes chemistry. When an icy body warms, internal pockets can melt temporarily. Liquids appear, reactions accelerate, and complex molecules rearrange. As the object cools again, those reactions slow or freeze, preserving their outcomes. This creates a pattern unlike anything on Earth's surface. Chemistry that turns on and off in pulses separated by long periods of dormancy. Such an environment is hostile to active, continuously metabolizing life, but it may be well suited to something else. Life does not need to be awake all the time. On Earth, many organisms already exploit dormancy. Seeds remain inactive for years. Bacteria survive extreme radiation by shutting down metabolism entirely. Tardigrades endure vacuum freezing and desiccation, reviving when conditions improve. These strategies demonstrate that continuity is not required, only repeatability. In a comet or asteroid, lifelike systems could exist as chemical networks that activate during brief windows of warmth, then persist in an inert state for millions of years. Each activation would not restart from scratch. It would resume from where the previous cycle left off. Over cosmic timescales, this stop-start process could still allow information to accumulate and selection to operate. The main obstacle is containment. Small bodies lack the gravity to hold dense atmospheres or oceans, but they are riddled with pores, fractures, and internal cavities. Ice and rock form natural compartments shielding chemistry from radiation and slowing diffusion. Within these microenvironments, molecules do not disperse instantly. They linger, they interact, they remember. This shifts the concept of habitability again. Instead of stable planet-wide environments, we are dealing with vast populations of tiny laboratories, each running slow, intermittent experiments in chemistry. Most fail, a few persist. Over time, rare configurations may become robust enough to survive repeated cycles of stress and dormancy. From afar, such systems would be almost impossible to detect. They would not alter atmospheres or emit obvious signals. Their presence would be statistical, not spectacular. A subtle bias in molecular distributions, an excess of complexity where simple chemistry should dominate. And this leads to a profound implication. If life can exist in this fragmented, intermittent form, then the absence of large, stable worlds does not eliminate the possibility of biology. It merely changes its tempo. Life becomes something that flickers, pauses and resumes, spread thinly across countless small bodies, rather than concentrated on a few planets. The universe in this view does not build life only where conditions are perfect. It experiments everywhere, allowing complexity to try fail and occasionally persist even in places that seem fundamentally unsuitable. But comets and asteroids still represent environments with solid matter and internal structure. They are not the most extreme test of the idea. To push this question to its limit, we must remove even that support. We must ask whether life could exist where matter itself is sparse, where there is no ground, no ice, no shell to hide within. That question takes us into the most counterintuitive environment of all, the vast molecular clouds between the stars. Between the stars lies a realm that appears almost empty. Light years across these regions contain no solid ground, no oceans, and no obvious sources of warmth. Temperatures hover just a few degrees above absolute zero. Matter is so diffuse that a cubic centimetre of space may contain only a handful of atoms. By everyday intuition, this is the opposite of a habitable environment. And yet these molecular clouds are among the most chemically active places in the universe. Within their cold interiors, atoms and simple molecules gather onto microscopic dust grains. Thin layers of ice accumulate, forming complex chemical surfaces. Cosmic rays penetrate deep into the cloud-breaking molecular bonds and triggering reactions that would be impossible under warmer conditions. Over time, surprisingly elaborate organic compounds assemble, some containing dozens of atoms arranged in intricate structures. These clouds are not static. They evolve slowly, folding and drifting under the influence of gravity and turbulence. Dense filaments persist for millions of years. Shockwaves pass through, compressing material and then releasing it again. Radiation fields vary gently across space, creating gradients that remain stable far longer than those on most planets. From the perspective of chemistry, this is not a void. It is a laboratory. The central challenge is density. Life as we know it thrives on frequent interactions. Molecules collide, react, and reorganize rapidly. In a molecular cloud, collisions are rare. Reaction times stretch from seconds to years or longer. At first, this seems fatal to the idea of life, but time behaves differently on cosmic scales. Molecular clouds persist for tens of millions of years. During that time, even extremely slow processes can accumulate meaningful outcomes. Reactions that would be negligible on Earth become significant when given enough duration. Complexity does not require speed, it requires persistence. The key lies in the dust grains themselves. Each grain acts as a microenvironment. Icy mantles trap molecules, keeping them close together. Surfaces provide catalytic sites, lowering energy barriers and enabling reactions that would otherwise never occur. Within these frozen shells, chemistry proceeds in a controlled, repeatable way. Molecules form, rearrange, and sometimes break apart, but the products remain nearby, ready for further interactions. These grains are not isolated. They drift through the cloud, experiencing different radiation levels, temperatures, and chemical surroundings. Over time, patterns emerge. Certain chemical networks prove more stable than others. Some arrangements survive repeated radiation strikes. Others collapse. Selection in a primitive form begins to operate. Information in this context is not encoded in genes but in structure. The arrangement of molecules on a grain surface influences which reactions occur next. Successful configurations persist, copied imperfectly, as material is exchanged between grains through collisions and shock events. This is not biology in any familiar sense. There are no cells, no metabolism, no reproduction as we understand it, but the core processes are present: energy input, structural persistence, variation, and differential survival. One of the most intriguing aspects of molecular clouds is their scale. A single cloud can contain material equivalent to millions of suns. Even if lifelike systems are extraordinarily rare within them, the sheer volume involved offers countless opportunities. Instead of a few habitable worlds, the universe provides vast regions where chemistry can explore complexity in parallel. Detecting such systems would be extraordinarily difficult. They would not announce themselves through atmospheric signatures or thermal emissions. Their presence would be statistical, subtle deviations in molecular abundances, unexpected correlations between compounds or chemical patterns that resist simple explanations. Yet these are exactly the kinds of anomalies astronomers already observe often without knowing how to interpret them. The possibility that molecular clouds could host proto-living systems does not imply that intelligence arises there, or that such systems ever evolve beyond chemistry, but it expands the boundary of where lifelike processes might begin. It suggests that the universe does not wait for planets to form before experimenting with complexity. If this is true, then life may not be something that appears suddenly on a finished world. It may be something that begins as a diffuse, fragile process spread across dust, ice, and darkness, long before any planet exists to shelter it. And that realization leads to a final, unavoidable question. If life can exist without planets, without stars, and even without solid matter, then what truly limits it? To answer that, we must look not at where life might arise, but at what threatens to erase it. That takes us to the deepest challenge of all: stability, information, and survival in a universe that constantly tries to pull everything apart. Once planets and stars are removed from the picture, energy becomes the central concern. Life does not require brightness, warmth, or even motion in the everyday sense. What it requires is access to a usable gradient, a difference that can be exploited repeatedly without immediately destroying the system that depends on it. On Earth, sunlight dominates because it is abundant and reliable. But it is not the only game in the universe. Everywhere matter exists, energy differences exist with it. Chemical reactions are the most obvious alternative. Whenever compounds with incompatible electron configurations come into contact, energy is released. In environments where oxidized and reduced materials mix slowly, chemical gradients can persist for immense periods of time. Water interacting with certain minerals produces hydrogen. Radioactive decay fractures molecules and creates reactive species. Even in cold environments, slow chemistry continues, driven not by heat but by quantum effects and radiation. These processes are not rare. They occur inside rocks, within ice, across dust grains, and along the boundaries between different phases of matter. They are quiet, gradual, and persistent. For lifelike systems, this steadiness can be more valuable than intensity. Another overlooked source of energy lies in radiation itself. Cosmic rays penetrate nearly every environment in the universe. They carry enormous energy and interact with matter in complex ways, breaking molecular bonds and creating cascades of secondary particles. While radiation is often seen as purely destructive, it is also creative. It drives chemistry forward, opens new reaction pathways, and generates energetic gradients at microscopic scales. In shielded environments beneath ice, inside pores, or within dense clouds, radiation becomes a controlled input rather than a lethal force. Systems that can repair or tolerate damage gain an advantage. Over time, this pressure favors stability and robustness, two traits central to any form of life. Magnetic and electric fields introduce yet another class of energy reservoirs. Charged particles confined by magnetic fields can store energy for long durations. When field lines reconnect, energy is released suddenly and locally. This happens in stellar atmospheres, planetary magnetospheres, and even in interstellar space. Plasma structures can persist, deform, and reorganize themselves in response to these fields, creating dynamic but patterned environments. Although such systems are far removed from chemistry as we know it, they demonstrate a broader principle. Energy can be stored, released, and regulated without solid matter or liquid solvents. In some cases, structure itself becomes the medium. The challenge once again is continuity. Energy sources that are too violent erase complexity. Sources that are too weak fail to sustain it. Life in any form must occupy the narrow region in between. It must tap into energy without exhausting it, exploit gradients without collapsing them, and maintain structure while constantly absorbing disturbance. In environments without planets, this balance becomes harder to achieve, but not impossible. What matters is not where the energy comes from, but whether it arrives in a way that allows systems to respond, adapt, and persist. Intermittent heating, slow chemical cycling, steady radiation flux, or periodic magnetic events can all in principle support long-term organization if their timing and intensity fall within the right range. This reframes habitability yet again. Instead of asking whether a place receives enough sunlight, we must ask whether it experiences repeatable energy flows. Instead of focusing on warmth, we must focus on gradients. Instead of stability alone, we must consider controlled disturbance, the kind that challenges systems without destroying them. By this measure, the universe is far less barren than it appears. Energy seeps into nearly every environment. The question is whether anything can learn to use it, and that question brings us to the most difficult obstacle facing life without planets. Not energy, not chemistry, but the problem of information, how it forms, how it persists, and how it avoids being erased in a universe that constantly favors disorder. That is the final barrier we must confront. Energy and chemistry alone are not enough. The universe is filled with energetic reactions and complex molecules, yet most of them fade into noise. What separates life from chemistry is not activity, but memory. Life must preserve information. It must retain patterns that worked in the past long enough for them to influence the future. And this requirement becomes brutally difficult once planets are removed from the equation. Planets are excellent at protecting information. They provide shelter compartments and scale. Rock pores, oceans, ice layers, and atmospheres all slow the relentless pull toward disorder. Without these features, information tends to dissolve. Molecules drift apart. Radiation scrambles structure. Gradients flatten. In open space, complexity is constantly under attack. This is the core challenge facing life without planets. To survive, any lifelike system must solve three related problems at once. It must create boundaries without walls, it must replicate patterns without stable containers, and it must resist erasure in an environment that favors dispersion. Nature, however, already offers partial solutions. Boundaries do not need to be solid. They can be statistical. Magnetic fields confine charged particles without physical barriers. Chemical films self-assemble at interfaces, forming membranes that exist only because conditions on either side differ. Even turbulence can generate long-lived vortices regions that maintain identity despite constant motion. In these cases, structure emerges not from rigidity but from balance. The boundary exists because forces cancel in just the right way. Such boundaries are fragile, but they can persist far longer than the intuition suggests. Replication too does not require DNA. At its most basic level, replication means that a pattern produces a similar pattern. Crystals do this naturally. Their lattice structure propagates as atoms attach themselves in repeating arrangements. Chemical reaction networks can do the same, reinforcing pathways that regenerate their own components. Even magnetic configurations can reappear when conditions repeat. What matters is not the molecule but the logic. A successful configuration increases the likelihood of its own recreation. In environments without planets, replication would be slow, imperfect, and distributed. There would be no organisms in the familiar sense, only patterns spreading through matter and energy. Some would fade quickly. Others would stabilize, copied again and again as conditions recur. Over long time scales, selection would favor patterns that resist disruption and recover quickly from damage. Radiation remains the greatest threat. High-energy particles tear apart molecules and scramble structures indiscriminately, but radiation also creates pressure. Systems that survive exposure gain an advantage. Shielding can emerge naturally. Ice layers, dust mantles, dense filaments, or simply statistical rarity, where only the most robust patterns persist because everything else fails. Information in this context becomes deeply encoded, not stored in a single place, but distributed across many interactions. Losing part of the pattern does not destroy it entirely. Enough remains to allow reconstruction. This is how resilience replaces fragility. Instead of one vulnerable genome, information is spread across a network of reactions, locations, or configurations. The system survives not because it is protected, but because it is redundant. From a distance, such life would be almost invisible. It would not build cities, forests, or atmospheres. It would not alter entire worlds. Its signature would be subtle, persistent complexity where none should exist. Patterns that reappear despite constant disruption. Chemical ratios that refuse to settle into equilibrium. Detecting this kind of life would challenge every method we currently use. We search for planets because planets amplify signals. Life without planets leaves whispers instead, and yet these whispers may be far more common. If information can persist without surfaces, without gravity wells, and without long-term shelter, then life is no longer confined to rare finished worlds. It becomes something that the universe continuously attempts, most of the time unsuccessfully, but often enough to matter. At this point, the question shifts again. It is no longer could life exist without planets. The more unsettling question becomes this. If life can exist in so many hidden forms, how much of it might already surround us completely unnoticed? Answering that does not require speculation alone. It requires reframing how we search, what signals we value, and what we are willing to recognize as alive. That realization brings us to the final step of this journey, one that forces us to reconsider not just where life exists, but how we define it in the first place. By this point, the question that opened our journey has quietly transformed. We began by asking whether life could exist without planets, but after stripping away surfaces, stars, oceans, and even solid ground, it becomes clear that the deeper issue is not location at all. It is definition. Planets feel special because they concentrate conditions, they compress matter trap energy, and create long-lived compartments where chemistry can refine itself. From a human perspective, they look like stages prepared for life to step onto. But the universe does not build with intention. It builds through processes, and those processes do not privilege planets. They merely exploit whatever structures happen to persist. Once that is understood, habitability stops being a map of places and becomes a spectrum of behaviors. Life in its most general form is not something that sits on a surface. It is something that happens wherever matter can remain organized while energy flows through it. Sometimes that organization takes the form of cells on a planet. Other times it may appear as slow chemical networks in ice-drifting reaction systems in clouds or patterns encoded in environments that never settle into solid ground. This perspective does not claim that such life is common, intelligent, or even long-lived in the way terrestrial life is. It makes a more restrained but more powerful claim. The universe does not forbid life outside planets. The laws of physics allow it, chemistry allows it, time allows it. What limits life, then, is not the absence of worlds, but the difficulty of sustaining information. Most environments erase patterns faster than they create them. Disorder dominates. Complexity flickers briefly and fades. Only in rare circumstances does organization survive long enough to be refined by selection. Planets are one of those circumstances, but they are not the only one. This realization reshapes the search for life beyond Earth. If life can exist without planets, then searching only for Earth-like worlds may be a profound form of bias. We may be tuning our instruments to the louder signals while ignoring quieter ones. We may be mistaking familiarity for likelihood. The universe may be filled with low-level distributed forms of life that never announce themselves with atmospheres or megastructures, but persist quietly wherever conditions permit. It also reframes a long-standing mystery. The apparent silence of the universe, the absence of obvious signs of extraterrestrial intelligence, may not mean that life is rare. It may mean that most life does not gather itself into planetary civilizations. It may remain diffuse, slow, hidden, and fundamentally alien to our expectations. In that sense, planets may represent not the most common homes for life, but the most visible ones. Standing back, the original question now feels almost inverted. Rather than asking how life could survive without planets, we might ask why planets produce such conspicuous life at all. Why does biology on Earth concentrate itself into organisms, ecosystems, and eventually minds capable of reshaping an entire world? Is that outcome typical, or is it an extreme case? Those questions point directly toward the next step in this series. If life does not require planets, and if it does not require sunlight, then the next boundary to examine is energy itself. How far can biology or biology-like processes drift from the familiar power sources that sustain us? Can life exist in complete darkness, powered only by chemistry radiation, or fields we barely notice? That question does not take us to a new place. It takes us to a new way of seeing, and it is there that the next chapter begins. For most of human history, life and light have felt inseparable. Every ecosystem we see begins with a star rising over a horizon. Plants stretch toward it. Animals follow the rhythms it sets. Seasons, climates, and biological cycles all trace back to a single brilliant source in the sky. From this perspective, it feels almost self-evident that life needs sunlight. Remove the star and the system collapses, yet this confidence rests on a narrow slice of experience. Sunlight dominates life on Earth, not because it is the only viable energy source, but because it is the most obvious one available on the surface. It floods the planet with power drives rapid chemical reactions and fuels complex food webs. But speed and brightness are not requirements for life. They are conveniences. The deeper requirement is far simpler and far less visible. Access to energy that arrives in a usable, repeatable way over long periods of time. Once that distinction is made, the sun begins to lose its special status. Beneath Earth's oceans, far below the reach of light, entire ecosystems thrive in permanent darkness. These environments are not marginal curiosities. They are stable, productive, and ancient. Their organisms do not photosynthesize. They do not depend on the sun even indirectly. Instead, they draw energy from chemical reactions between water and rock, converting invisible gradients into living structure. For millions of years, these systems have persisted without ever experiencing a sunrise. This alone should unsettle the idea that light is fundamental. Sunlight is powerful, but it is also chaotic. Stars flare, radiation spikes, stellar life cycles impose deadlines on their surrounding worlds. Over long timescales, starlight is not gentle. It is disruptive. Life on Earth survives this volatility because the planet absorbs buffers and redistributes solar energy. through atmosphere, oceans, and geology. The star is filtered. Without that filtering, raw stellar energy would be hostile rather than helpful. Remove the planet and the sun becomes dangerous. This inversion matters because it reveals a hidden bias in how we think about habitability. We often ask whether a world receives the right amount of starlight, but rarely ask whether it can survive that light in the first place. We treat darkness as absence rather than as a different regime, one with its own advantages. In the absence of sunlight, environments become quieter, temperature swings slow, radiation exposure drops, chemical systems experience fewer resets, evolution instead of racing drifts. In such settings, survival favors durability rather than speed, efficiency rather than expansion. These are not inferior traits. Over cosmic timescales, they may be superior ones. The universe itself seems to agree. Most matter does not orbit stars closely. Most environments exist far from steady illumination. Vast regions of space never experience direct starlight at all, yet energy still flows through them. Radioactive decay releases heat from within. Chemical gradients persist wherever incompatible materials meet. Cosmic rays and weak radiation field provide a constant low-level input that never truly shuts off. These sources are unimpressive by human standards. They do not light skies or warm surfaces, but they share one critical property: longevity. Unlike stars, they do not burn out quickly or change violently. They operate quietly, reliably, and for billions of years. From the perspective of life, that reliability may matter more than intensity. If biology is a process of extracting order from energy flows, then any environment that offers stable gradients becomes a candidate habitat. Light is only one way to create such gradients. Chemistry can do the same. So can heat. So can radiation. So can differences in pressure composition or electrical potential. None of these require a star overhead. Seen this way, the sun begins to look less like the source of life, and more like one option among many. Earth's biosphere evolved to exploit light because light was abundant and accessible. But evolution does not aim for universality, it aims for sufficiency. If other worlds or other environments offer energy in darker, quieter forms, life there would simply adapt to those conditions instead. This reframes a question that has guided decades of exploration. Instead of asking where starlight is strongest or most Earth-like, we should ask where energy flows persistently enough to support organization. Instead of mapping habitable zones around stars, we should consider the much broader category of energy-accessible environments. Places where gradients endure, chemistry remains active, and information can accumulate slowly over time. Once that shift occurs, the universe looks very different. Darkness stops being an obstacle. It becomes a clue, and to follow that clue we must set aside light entirely and examine what truly powers life at its most fundamental level. Not photons, but gradients themselves. That is where the next stage of this journey begins. Before life can exist, energy must already be moving, not flowing wildly, not exploding outward, but slipping steadily from one state to another, creating differences that can be tapped again and again. This is the foundation beneath every living system we know, whether it depends on sunlight or not. Life does not feed on energy itself, it feeds on imbalance. On Earth, sunlight creates that imbalance by heating the surface unevenly. Warm regions drive winds. Light fuels chemical reactions that build sugars and release oxygen. From this single source, a cascade of gradients emerges. Temperature, chemistry, pressure, and motion all become linked. Biology inserts itself into that cascade, siphoning off a fraction of the flow. But sunlight is only one way to start this process. In physical terms, a gradient is simply a difference that wants to disappear. Hot flows toward cold. Reactive chemicals combine into stable ones. Charged particles move toward neutrality. Every time such a difference exists, energy is released along the way. If a system can intercept that release, slow it down, redirect it, or store part of it, complex behavior becomes possible. This principle holds everywhere, not just on illuminated worlds. Deep underground heat leaks outward from planetary interiors. Along the way, it creates zones where minerals interact, dissolve, and reform. In these regions, chemistry never fully settles. Reactions remain slightly out of balance, sustained by a slow but relentless energy flow. Life, when it appears in such places, does not depend on light at all. It depends on the persistence of the gradient. Chemical gradients are especially powerful because they can last far longer than thermal ones. When oxidized and reduced materials remain separated by rock layers, ice barriers, or simple geometry, energy is locked in place. As long as diffusion is slow, the imbalance survives. Systems that learn to exploit that separation gain a steady supply of usable energy without ever seeing a photon. Radiation creates gradients too, though in a subtler way. Low-level radiation constantly breaks molecular bonds, pushing chemistry away from equilibrium. Most of the time this disruption is seen as destructive, but destruction is not the same as randomness. Bond breaking opens new pathways. It creates reactive fragments that can recombine in unexpected ways. Given enough time and enough repetition, these processes generate complexity rather than erase it. Even electrical and magnetic fields form gradients capable of doing work. Charged particles confined by fields store energy spatially. When conditions shift, when fields weaken, reconnect, or rearrange, the energy is released locally. In plasma-rich environments, such processes happen continuously, creating dynamic but structured regions, where energy cycles through predictable patterns. What all of these examples share is independence from light. They do not require a star. They do not depend on day-night cycles or surface illumination. They operate wherever matter exists in an uneven state. And because unevenness is the default condition of the universe, gradients are far more common than sunlight. This changes how we should think about the origins of life. Instead of imagining a dark, inert universe waiting passively for stars to ignite, we should picture a cosmos already threaded with slow energy flows. Heat leaking from radioactive interiors, chemistry unfolding on cold surfaces, radiation stirring reactions in places too dim for warmth. Long before planets form stable climates, these processes are already at work. Life in this view does not appear because conditions become perfect. It appears because conditions never fully settle. The most important question is no longer whether enough energy is present. It is whether that energy arrives in a form that can be intercepted without destroying the system that intercepts it. Too violent and structure shatters. Too weak and nothing accumulates. The narrow region between those extremes is where organization survives. Sunlight often pushes systems toward the violent end of that spectrum. It accelerates reactions, amplifies fluctuations, and increases exposure to radiation. In contrast, non-luminous energy sources tend to operate quietly. They impose fewer shocks. They allow chemistry to proceed at a pace that favors stability. Over billions of years, that difference matters. Evolution does not reward speed in the long run. It rewards persistence. Systems that can endure subtle, continuous energy flows have more opportunities to refine themselves than systems constantly reset by intense disturbances. Once we accept that gradients, not light, are the true currency of life, the range of possible habitats expands dramatically. Worlds without stars no longer seem sterile. Dark environments no longer feel empty. They simply operate on different tempos. And with that understanding in place, we're ready to examine one of the clearest demonstrations of life without sunlight that already exists, right here in our own biosphere. Not as an exception, but as a proof of concept. Long before scientists seriously considered life beyond Earth, our own planet had already provided a quiet demonstration that sunlight is optional. Far beneath the ocean surface, beyond the reach of even the faintest glow, entire ecosystems flourish in complete darkness. These environments are not fueled by photosynthesis. They are powered by chemistry, and their existence changes the rules of habitability in a fundamental way. At the heart of these systems lies a process known as chemosynthesis. Instead of capturing photons, organisms harness energy released when certain chemicals react with one another. Hydrogen sulfide methane ion compounds and other reduced materials flow upward from Earth's interior through cracks in the seafloor. When these compounds encounter oxygenated seawater, a chemical imbalance appears. Energy is released. Life inserts itself into that release, redirecting part of the flow into growth, repair, and reproduction. No sunlight is involved at any stage. These ecosystems are not fragile anomalies. Many have persisted for millions of years. They support complex food webs, including large multicellular organisms. Their productivity rivals that of some surface ecosystems despite operating on far weaker energy inputs. What they lack in intensity, they compensate for with stability. The crucial lesson here is not that life can survive without light. It is that life can be built entirely on chemical gradients between rock and water. This mechanism is not unique to Earth. Wherever liquid interacts with certain minerals, chemistry is driven out of equilibrium. One of the most important reactions in this context involves water, an iron-rich rock producing hydrogen gas. This process, known as serpentinization, occurs spontaneously under a wide range of conditions. It releases energy steadily and predictably. On Earth, it happens deep underground and beneath the ocean floor. Elsewhere, it could occur inside icy bodies, subsurface oceans, or rocky interiors completely isolated from any star. In these environments, light is not merely absent, it is irrelevant. The energy that sustains the system comes from the planet or object itself. As long as water and reactive minerals remain in contact, the gradient persists. Time becomes the decisive factor. The slower the system changes, the longer life has to adapt to it. This has profound implications for worlds beyond Earth. A body does not need to orbit a star to host chemosynthetic life. It does not even need a surface. It needs only three things: liquid water, chemically reactive materials, and enough internal energy to keep reactions going. These conditions may exist in places we would never label as habitable. Deep beneath ice, inside drifting objects, or within isolated fragments of rock. Such biospheres would be hidden by design. They would produce no atmospheric signatures. They would emit little heat. Their activity would be localized, slow, and shielded. From afar, they would look inert, yet inside chemical cycles could be running continuously, supporting life that has never known light or sky. Evolution in these environments would follow a different trajectory. Without sunlight, there's no incentive to grow quickly or spread widely. Selection would favor efficiency, resilience, and tight coupling to local chemistry. Life would become conservative rather than expansive. It would adapt to its niche with precision, not ambition. This may help explain something often overlooked. On Earth, the most ancient branches of the tree of life are dominated by organisms that thrive in dark, chemically rich environments. Photosynthesis appears later. Light-based ecosystems may be an evolutionary shortcut, a rapid way to access energy, but not the original or most robust foundation for life. If that is true, then chemosynthesis is not a marginal curiosity. It may represent the default mode of life in the universe, a mode that does not require stars, a mode that does not care about day or night, a mode that operates wherever rock, water, and time intersect. Once this is understood, the idea of life without sunlight no longer feels exotic. It feels inevitable, and that realization leads directly to the next question. If chemistry alone can power entire biospheres, how far can this principle be pushed? Can even weaker, quieter energy sources sustain life over cosmic timescales? To answer that, we must look deeper into heat that never turns off, and worlds warmed from within rather than from above. There is a source of energy that does not flicker, does not flare, and does not care whether a world faces a star. It operates quietly deep within matter itself. Radioactive decay is often associated with danger and destruction, but in planetary science it plays a very different role. It is one of the most reliable heat engines in the universe. Certain elements release energy simply by existing, breaking down at predictable rates over billions of years. They do not require ignition. They do not exhaust themselves quickly. They just keep going. On Earth, this process is easy to overlook because sunlight dominates the surface. Yet far below our feet, radiogenic heat drives much of the planet's long-term behavior. It keeps the mantle warm, it fuels volcanism, it sustains tectonic activity. Even if the sun was suddenly removed, Earth's interior would remain warm for an immense span of time. This matters because heat, like light, is only useful to life when it creates gradients. Inside a solid body, radiogenic heating produces slow but persistent temperature differences. Warm regions lie next to cooler ones. Water circulates. Minerals dissolve and reform. Chemical reactions are nudged forward again and again. Nothing explodes. Nothing resets. The system simply refuses to reach equilibrium. In worlds without sunlight, this kind of energy is ideal. A planet moon, or even a large rocky fragment drifting through interstellar space, can remain internally active long after its surface freezes solid. A thick outer layer of ice or rock acts as insulation, trapping heat inside and shielding the interior from radiation. Beneath that shell, liquid water can persist. Chemistry continues. Time stretches forward undisturbed. From the perspective of life, this environment is not impoverished. It is protected. Radiogenic heat does not vary wildly. It does not impose seasons or cycles that force rapid adaptation. Instead, it creates a background condition of stability. Evolution in such a setting would be slow, but it would also be relentless. Given enough time, even weak gradients become powerful drivers of organization. This changes how we think about habitable lifetimes. Stars evolve. They brighten, dim, and eventually die. Their habitable zones shift. Worlds dependent on stellar energy must adapt or perish. Radiogenic heat, by contrast, follows a long, predictable decline. For billions of years, it remains strong enough to sustain internal activity. A biosphere powered from within may outlast one powered from above. There is another advantage as well. Because radiogenic energy originates inside matter, it is naturally coupled to chemistry. Heat promotes reactions. Reactions release and absorb heat. Feedback loops form. In these loops, energy and chemistry reinforce one another, creating conditions that favor persistence over expansion. Such biospheres would never be visible from space. They would not paint atmospheres with oxygen or methane. They would not alter planetary albedo. Their activity would be buried silent and self-contained, and yet they might represent some of the longest-lived living systems in the universe. This possibility pushes the concept of life without sunlight further into realism. It suggests that darkness is not merely survivable but potentially optimal. A world that never sees a star may offer life something rare. Uninterrupted continuity, no stellar flares, no climate collapse, no cosmic deadlines imposed from the outside. If evolution values anything, it is time. Radiogenic heat offers time in abundance, and once we accept that life can be powered quietly from within, another pattern begins to emerge. Many of the safest environments in the universe may be hidden, one's places shielded from radiation, light and chaos. That insight leads us to an even broader realization. Perhaps most life does not live where the universe is brightest. Perhaps it lives where conditions are calmest. To explore that idea, we must move deeper, still below surfaces beyond exposure, into biospheres that exist entirely out of sight. Surface environments feel inviting because they are visible. They offer light, open space and dramatic change. But from a biological perspective, surfaces are also the most dangerous places to live. They are exposed to radiation, temperature extremes, impacts and chemical instability. On cosmic timescales, surfaces are kill zones, regions where life must constantly recover from disruption. Below the surface, the story changes completely. Subsurface environments are quieter, temperature fluctuations are muted, radiation drops sharply with depth. Chemical conditions evolve slowly rather than violently. These traits make underground habitats not marginal refuges, but potentially the most stable biological niches available. On Earth, this reality is already well established. Microbial life has been found kilometers beneath the surface, living within rock pores, fractures and aquifers. These organisms do not rely on sunlight, oxygen or surface nutrients. They derive energy from chemical reactions involving minerals and water. Some may have been isolated for millions of years, evolving in near-total darkness without ever interacting with the surface biosphere. What matters here is not the specific organisms, but the principle they demonstrate. Life does not need exposure, it needs continuity. Subsurface environments provide natural containment. Rock acts as both barrier and scaffold. Pores create compartments. Fluids move slowly, carrying energy and nutrients without flushing systems into chaos. Information, biological or chemical, can persist because the environment does not constantly reset itself. This makes underground habitats particularly important for worlds without sunlight. If a planet, moon, or drifting body lacks a star, its surface will almost certainly be hostile, frozen, irradiated, or both. But below that surface, conditions may be far more forgiving. Heat from radioactive decay or residual formation energy leaks outward, creating zones where liquid can exist. Chemistry becomes active, gradients persist. In such worlds, life would never appear on the surface at all. There would be no forests, no oceans open to the sky, no visible biosphere. Everything living would be hidden, sealed away beneath layers of ice and rock. From the outside, the world would look inert. From the inside, it could be biologically rich. This inversion has profound implications. We often assume that if life exists somewhere, it will eventually reveal itself. It will alter the atmosphere. It will leave chemical fingerprints. It will announce its presence. But subsurface life does none of these things. It is quiet by design. It survives by avoiding attention, not attracting it. In a universe filled with radiation and instability, this strategy may be the most successful one. Over billions of years, surface ecosystems rise and fall. Ice ages come and go. Stars flare. Climates shift. Meanwhile, subsurface systems persist largely unaffected. They do not need to adapt quickly because they are rarely challenged. Evolution in such environments would proceed differently. Without sunlight, there is no advantage to rapid growth or expansion. Energy is limited but reliable. Selection favors efficiency, repair, and tolerance rather than speed. Organisms or lifelike systems become conservative. They change slowly, but they endure. If this pattern holds beyond Earth, then much of the universe's life may be invisible to us, not because it is rare, but because it is buried. Entire biospheres could exist beneath frozen shells, inside rocky interiors, or within drifting objects powered quietly by chemistry and heat. They would leave little trace on the surface. They would not produce signals designed to be seen. Our telescopes focused on light and atmospheres would simply look past them. This realization forces a shift in perspective. Habitability may not peak at the surface of worlds, but beneath them. The safest place for life may be the place least affected by the outside universe. Darkness shielding and isolation conditions we instinctively associate with lifelessness may actually be signs of biological resilience. If so, then the absence of visible life on a world tells us very little. It may simply mean that life has chosen the safer path. And once we accept that darkness and burial can be advantages rather than limitations, the next step becomes unavoidable. If life thrives best where disturbance is minimized, then perhaps the absence of light is not a weakness at all. Perhaps it is a feature. That idea takes us to the heart of the next question: why darkness itself may be one of the most favorable conditions for life anywhere in the universe. Darkness is often described as an absence. No light, no warmth, no activity. In everyday experience, it feels like a lacquer sign that nothing important is happening. But in physical terms, darkness is not emptiness. It is a reduction in disturbance. And for life, disturbance is often the true enemy. Light brings energy, but it also brings instability. On illuminated worlds, energy arrives in bursts. Stellar flares spike radiation levels. Day-night cycles force constant adjustment. Seasons reshape entire ecosystems. Over long timescales, stars evolve, altering climates and pushing biospheres toward collapse or reinvention. Life on the surface survives by adapting quickly or dying often. In darkness, those pressures vanish. A world without sunlight does not experience weather in the familiar sense. Temperatures change slowly. Radiation levels are low and steady. Chemical systems are not repeatedly reset by external shocks. The environment becomes predictable, not because it is simple, but because it is calm. From an evolutionary standpoint, this calm is powerful. Selection does not require drama. It requires consistency. In a quiet environment, even small advantages matter because they are not overwhelmed by noise. Repair mechanisms outperform speed. Stability outcompetes expansion. Life does not need to race. It only needs to persist slightly better than its alternatives. This shift in tempo changes everything. On Earth's surface, rapid energy input encourages complexity that is fast, flexible, and fragile. In the dark, complexity may emerge more slowly, but it can become deeply entrenched. Systems have time to explore subtle configurations, refining themselves over millions or billions of years without being wiped clean. Darkness also reduces one of the greatest threats to life: radiation damage. Without constant exposure to high-energy photons, molecular structures last longer. Information decays more slowly. Repair processes do not need to be aggressive or costly. Over time, this favours life forms or lifelike systems that are conservative rather than extravagant. This suggests a counterintuitive possibility. The most common form of life in the universe may not be vibrant, visible, or active in ways we recognise. It may be slow, quiet, and deeply embedded within stable environments. It may never develop features designed to interact with light, because light is simply not part of its world. Such life would not build towering ecosystems or rapidly diversify. It would not reshape planets. Instead, it would persist subtly, modifying its surroundings in ways too small to notice from afar. From our perspective, this kind of biosphere would appear lifeless, and that appearance would be misleading. If darkness is an advantage, then the universe's most biologically productive regions may be its dimmest ones. Deep interiors, shielded oceans, isolated fragments drifting through space. Places where energy flows gently and relentlessly, unperturbed by external chaos. This reframes the idea of habitability yet again. Instead of asking where life can flourish dramatically, we should ask where it can endure quietly. Instead of looking for bright signatures, we should search for stability. Darkness becomes not a sign of absence, but a clue, a marker of environments where life is least likely to be erased. The implications are unsettling. It means that many of the worlds we dismiss as dead may simply be too calm to announce themselves. Their life, if present, has no incentive to reach outward or leave obvious traces. It exists for itself, not for observers. And if that is true, then our methods of detection are fundamentally biased. We look for light because light is how we live. But life elsewhere may have learned a different lesson, that survival favours silence over spectacle. To understand how far this lesson can be taken, we must now confront the most unfamiliar energy sources of all. Not chemistry, not heat, but forces that operate beneath our everyday intuition. Fields, plasmas, and gradients so subtle that they are almost invisible. That is where the next stage of this exploration leads. Once light, heat, and chemistry are set aside, the remaining energy sources feel almost abstract. They do not glow. They do not warm surfaces. They do not even announce themselves clearly. Yet they shape vast regions of the universe and move enormous amounts of energy every second. These are the fields and forces that operate quietly beneath everyday intuition. Electric fields, magnetic structures, plasmas, and weak but persistent interactions that never fully switch off. At first glance, they seem inhospitable to life. There are no oceans to dissolve molecules, no rocks to anchor reactions. Matter is sparse, energetic, and often unstable. For a long time, these environments were dismissed entirely in discussions of habitability, not because physics forbade life there, but because biology had no familiar foothold. But familiarity is not a physical law. Electric and magnetic fields are capable of storing energy spatially. Charged particles trapped within them follow predictable paths, forming stable configurations that can persist for long periods. In planetary magnetospheres, radiation belts maintain structure for years or longer. In interstellar space, magnetic fields guide the motion of charged particles across light years, shaping filaments and boundaries that resist diffusion. These structures are not random. They form because forces balance. Particles move, but they move within constraints. Energy circulates rather than dissipates immediately. In some cases, disturbances propagate as waves, carrying information through the system without destroying it. Plasma, the most common state of matter in the universe, adds another layer of complexity. It is not simply gas, but a collective system in which particles interact through fields as much as through collisions. Plasmas can self-organize, forming filament sheets and long-lived patterns that respond coherently to external inputs. From a distance, these patterns look chaotic. Up close, they follow rules. The question is not whether such environments resemble life as we know it. They do not. The question is whether they can support processes that meet the minimal criteria for lifelike behavior. energy flow, structural persistence, feedback, and selective survival. In principle, they can. A configuration of charged particles that persist longer than alternatives has an advantage. A structure that redistributes energy in a way that stabilizes itself resists decay. When disturbances occur, some patterns recover while others collapse. Over time, selection operates not on organisms but on configurations. This is not biology in the classical sense. There are no cells, no metabolism, no reproduction through division. But the logic of persistence remains. Information is encoded not in molecules but in field structures and particle distributions. Memory exists as pattern stability. The most important constraint is timescale. These systems evolve quickly compared to geological processes but slowly compared to molecular reactions. Their dynamics fall into an intermediate regime fast enough to respond, slow enough to accumulate change. In that regime, complexity can emerge without immediately dissolving into noise. Would such systems ever become truly alive? That question may be poorly framed. Life is not a binary state. It is a spectrum of organization. At one end lie simple chemical cycles. At the other lie ecosystems and intelligence. Between them exist countless intermediate forms that blur the boundary between physics and biology. Field-based or plasma-mediated lifelike systems, if they exist, would occupy that middle ground. They would not resemble organisms. They would resemble processes' persistent adaptive patterns embedded in energy flows rather than matter. Detecting such systems would be extraordinarily difficult. They would leave no chemical fingerprints, no atmospheres, no surfaces to analyze. Their signatures would be dynamical rather than material unexpected stability, recurring patterns, or anomalous energy distributions that resist simple explanation, and yet the universe is already filled with structures like these. We observe filaments that maintain coherence over immense distances. We see plasma waves that propagate without dissipating. We detect magnetic boundaries that survive repeated disturbances. We study them as physics, not biology, because we lack the language to describe them otherwise. But language does not constrain reality. If life can exist without light, without planets, and without chemistry as we know it, then the universe's capacity for organization is far greater than we usually allow. The boundary between living and non-living becomes less a line and more a gradient. This realization does not diminish the significance of biology. It expands it, and it prepares us for the final challenges of this exploration, not where life might exist, but how we could ever recognize it when it does. Because once life abandons light matter and surfaces detection becomes the hardest problem of all, that problem defines the next stage of this journey. Without sunlight, evolution does not stop. It slows, it redirects, and it reshapes itself around different pressures, but the underlying logic remains intact. Variation still appears. Environments still favor some configurations over others. Information still accumulates provided it can persist long enough to matter. Light accelerates evolution, but it does not define it. In dark environments, the dominant pressure is not competition for energy, but efficiency in using it. Energy sources such as chemical gradients, radiogenic heat, or weak radiation fluxes are limited but steady. Systems that waste energy collapse quickly. Systems that recycle efficiently endure. Over long spans of time, this favors simplicity, robustness, and tight coupling between structure and function. Evolution becomes conservative rather than explosive. This is not a disadvantage. On Earth, many of the most resilient organisms are not the fastest or most complex. They are the ones that tolerate extremes, repair damage slowly but reliably, and persist when conditions change only slightly. In darkness, these traits become central rather than peripheral. Mutation in this context looks different as well. Without intense radiation or rapid replication, changes occur gradually. Errors accumulate slowly. This reduces catastrophic failure while allowing subtle improvements to persist. Selection has time to evaluate small advantages over millions of years. Complexity grows not through sudden leaps but through careful refinement. The absence of light also reshapes ecological interactions. There are no photosynthetic producers flooding the system with energy. Instead, energy enters the biosphere at specific interfaces where rock meets water, where chemistry remains unbalanced, where heat leaks outward. These entry points are limited. As a result, ecosystems organize around them tightly. Waste is recycled efficiently. Niches are narrow and stable. Predation, if it exists at all, would be rare and constrained. Cooperation, or at least coexistence, becomes more advantageous than competition. Systems that destabilize their environment risk eliminating their own energy source. In such settings, evolution favors restraint. Time becomes the most important variable. Dark biospheres may evolve more slowly than surface ecosystems, but they also avoid frequent extinction events. They are not exposed to impacts, flares, or climate collapse. Over billions of years, even slow rates of change produce profound outcomes. What matters is not speed, but uninterrupted duration. This raises a subtle but critical possibility. Life without light may be older on average than life dependent on stars. Stars have lifetimes. They form, evolve, and die. Dark environments powered by internal heat or chemical gradients can persist before stars ignite and after they fade. Life that emerges in such settings may predate surface life and outlast it by enormous margins. If intelligence ever arises in these environments, it would do so under very different pressures. There would be no incentive to perceive light-build visual systems or explore open space. Information processing would focus inward on chemistry gradients and long-term stability. Awareness, if it exists, would be shaped by slow change rather than rapid events. But intelligence is not required for significance. Even simple, persistent, lifelike systems alter their surroundings. They lock energy into structured pathways. They create chemical disequilibria that endure. Over time, these effects compound, subtly reshaping their environments without ever becoming visible from the outside. This makes detection extraordinarily difficult. Dark evolved systems leave few obvious traces. They do not announce themselves with atmospheric changes or large-scale energy output. Their presence is inferred indirectly, if at all, through anomalies, patterns that resist equilibrium longer than expected. Recognizing such life requires a shift in perspective. We must stop expecting evolution to look fast, dramatic, or directional. In the dark, evolution looks patient. It advances through persistence rather than conquest. It values survival over dominance. And that realization leads to a sobering conclusion. If life commonly evolves without light, then much of the universe's biological history may be unfolding at a pace, and in a form that we are poorly equipped to notice. To find it, we must rethink not only where we search, but how we interpret what we see. That challenge brings us to the final problem of life without sunlight, the problem of detection itself. If life thrives without sunlight, then most of our search strategies are aimed in the wrong direction. Modern astrobiology is built around visibility. We look for planets reflecting starlight. We analyze atmospheres backlit by stars. We search for gases that should not coexist in equilibrium under illumination. Oxygen, methane, ozone. All of these signals assume a biosphere that interacts with light and modifies a planet's exterior. Dark life does none of that. A biosphere powered by chemistry, radiogenic heat, or weak radiation has no reason to reshape an atmosphere. It may not even have access to one. Its activity is buried, localized, and slow. From the outside, the world appears inert. Spectra look clean. Temperatures look uniform. Nothing seems out of place. This creates a profound observational blind spot. Our instruments are optimized to detect excess. Too much heat, too much gas, too much motion. Dark biospheres produce none of these in dramatic quantities. Their signatures are subtle imbalances, often smaller than the uncertainties in our models. Signals that blend into background noise rather than standing out from it. Even when anomalies appear, they're easy to dismiss. A slight excess of hydrogen here, an unexpected ratio of isotopes there, a thermal pattern that does not quite fit expectations. Each can be explained away as geology, chemistry, or instrumental error. Without a guiding framework that expects life in darkness, we default to non-biological explanations, and in most cases those explanations are sufficient. The challenge is not that dark life leaves no traces. It is that its traces resemble non-life too closely. Chemical reactions driven by rock and water can mimic metabolic byproducts. Radiogenic heating can explain temperature gradients. Radiation-driven chemistry can generate complexity without biology. Distinguishing between these possibilities requires more than detection. It requires interpretation. This problem grows even harder at interstellar distances. Subsurface biospheres do not alter albedo. They do not emit characteristic light. Their heat output is diluted across thick insulating layers. Any signal they produce is filtered, delayed, and weakened before it reaches space. By the time it escapes, it looks ordinary. From a telescope's perspective, nothing is wrong. This forces a reconsideration of what counts as evidence. Instead of searching for specific molecules, we may need to search for persistence. Patterns that remain stable longer than physical models predict, chemical systems that resist equilibrium across geological timescales, correlations that appear repeatedly in environments where randomness should dominate. These are statistical signatures, not visual ones. They require long-term observation, comparative analysis, and theoretical humility. They demand that we accept uncertainty rather than eliminate it, and they challenge the expectation that life announces itself clearly. In a universe where darkness favors stability, silence may be the dominant mode of biology. This has unsettling implications for one of the most famous questions in science. If life without sunlight is common, then the apparent emptiness of the universe, the lack of obvious signals, no longer implies rarity. It implies invisibility. We may be surrounded by living systems that never broadcast, never expand outward, and never alter their environments in ways we recognize. They exist for themselves, not for observers. In that context, the absence of detection becomes ambiguous. It no longer tells us whether life is rare or abundant. It tells us only that our methods are tuned to the wrong kind of life. This realization reframes the search for life as a problem of expectations rather than technology. We may already have the data we need. What we lack is the willingness to interpret quiet anomalies as potential signs of organization, rather than dismiss them as noise. We look for fireworks while life may be whispering, and once that possibility is acknowledged, the final step becomes unavoidable. If life does not follow light, and if it hides where our instruments struggle to see, then our definition of life itself may be incomplete. The last question then is not where life exists or how it is powered. It is whether we would recognize it at all if we did. By the end of this journey, the role of sunlight has quietly diminished. What once felt like a prerequisite now looks more like a historical convenience, an abundant energy source that shaped life on Earth, but not one that defines life everywhere. Strip away stars' illumination and warm surfaces, and the core logic of biology remains intact. Energy still flows. Gradients persist. Information can still accumulate. Life does not require light. It requires opportunity. Throughout the universe, energy moves in subtle ways. Heat leaks from radioactive interiors. Chemical imbalances endure where water meets rock. Radiation stirs reactions even in the coldest darkness. Fields store and release energy without ever producing a glow. These processes operate continuously long before stars ignite and long after they fade. In such environments, life would not evolve to be seen. It would not paint atmospheres or sculpt landscapes. It would not signal its presence through brightness or expansion. Instead, it would optimize for endurance. It would bury itself, slow its metabolism, and couple tightly to whatever energy source remained reliable. Darkness would not be an obstacle to overcome. It would be a feature to exploit. This perspective overturns a deep assumption. We often imagine life as something that spreads outward, transforming its surroundings and leaving unmistakable traces. But that vision is shaped by surface biology, by ecosystems exposed to light and change. In quieter environments, success may look very different. Survival favors restraint. Growth gives way to persistence. Silence becomes adaptive. If that is the case, then the universe may be far more alive than it appears. Not because it is filled with civilizations or dramatic biospheres, but because it allows organization to persist wherever disturbance is minimized. Life may be woven into the fabric of dark interiors, drifting bodies and shielded regions we rarely consider. It may exist at scales and tempos that evade our expectations. This does not diminish the significance of Earth's biosphere. It contextualizes it. Life on the surface of a sunlit planet may be one of the loudest expressions of biology, but not the most common one. It may represent an extreme case shaped by intense energy input and rapid change. Elsewhere, life may choose a quieter path. Recognizing this requires humility. It demands that we accept the possibility that life does not announce itself, does not progress toward complexity as we define it, and does not share our priorities. It may never build technology. It may never look outward. It may simply persist, refining itself slowly in places where nothing dramatic ever happens. And yet persistence is the deepest triumph over entropy the universe allows. If life can exist without planets, and if it can thrive without sunlight, then the final boundary we must examine is not location or energy, but familiarity. Are we searching only for life that resembles us? Are we ignoring forms of organization that operate beyond our definitions? Are we mistaking difference for absence? These questions point directly to the next stage of this exploration. If life can abandon worlds and stars, then perhaps it can also abandon the chemistry we know best. Perhaps the most invisible life is not hidden by darkness, but by unfamiliarity. That leads us to the final chapter of this series, life that does not look like life at all. Life as we search for it is expected to announce itself. We imagine movement growth color chemistry in motion. We look for atmospheres out of balance surfaces reshaped by biology signals that rise above their surroundings and demand attention. Even when we claim to be open-minded, our expectations remain anchored to one quiet assumption. If something is alive, it should look alive to us. That assumption has never been tested outside Earth. Every example of life we know comes from a single environment shaped by a single star unfolding on the surface of a single planet. Visibility is not an accident here. It is a consequence of exposure. Sunlight floods the surface with energy. That energy drives fast chemistry, rapid growth, and large-scale ecological change. Life becomes loud because the environment rewards loudness. But visibility is not a universal property of life. It is a local outcome. Strip away light surfaces and open environments and the incentives change completely. In quiet settings, drawing attention is not an advantage. Altering your surroundings is not a success metric. Survival favors integration rather than disruption. The most successful systems are those that blend in so well they are indistinguishable from their environment. From a physical standpoint, this makes sense. Any organized system that stands out is easier to destroy. High contrast invites interference. Strong signals attract disturbance. Over long timescales, persistence belongs to structures that minimize their footprint, not maximize it. Life that learns this lesson early may never become visible in the ways we expect. This creates a fundamental mismatch between how life may exist and how we look for it. Our detection strategies assume excess, too much oxygen, too much heat, too much motion. We search for planets that are chemically loud and dynamically unstable, because that is what Earth looks like from a distance. But Earth is not a template. It is a case study shaped by specific circumstances. Visibility in this sense is a bias. We confuse detectability with likelihood. We assume that the most noticeable forms of life are the most common ones. Yet in every other domain of science, the opposite is usually true. The loudest phenomena are rarely the most abundant. They are simply the easiest to observe. Consider how much of Earth's own biosphere would be invisible from afar. Subsurface life leaves no atmospheric signature. Deep ocean ecosystems barely affect global chemistry. Microbial communities dominate biomass but produce weak, ambiguous signals. Even here on a planet saturated with life, most biology operates quietly and goes unnoticed unless we look very closely. Now scale that problem to the galaxy. Imagine forms of life that never reach the surface, never interact with light, and never modify their environment beyond what physics already allows. They do not create oxygen. They do not alter albedo. They do not build structures that persist on planetary scales. Their activity is local, slow, and deeply embedded. From our perspective, nothing is happening. Yet from theirs, existence continues uninterrupted. This forces a subtle but profound realization. Life does not need to reveal itself to be successful. In fact, revelation may be a liability. A system that remains chemically and energetically indistinguishable from its surroundings is harder to disrupt. Over billions of years, that advantage compounds. Visibility becomes optional. Invisibility becomes adaptive. Once this possibility is taken seriously, the search for life changes direction. The question is no longer where would life look obvious, but where could organization persist without being noticed? The answer to that question does not point to bright surfaces and dramatic atmospheres. It points inward, downward, and sideways into environments where signals blur into background and structure hides inside structure. The universe may be filled with such places. If so, then the absence of obvious life does not imply emptiness. It implies that we are asking the wrong question with the wrong tools, guided by expectations shaped by a single unusual example. The real challenge is not finding life, it is recognizing it. And recognition becomes almost impossible once we realize that our definition of life may already exclude most of the things we're trying to find. That realization leads directly to the next problem, one even more limiting than visibility. What if life does not merely hide from our instruments, but falls completely outside the definitions we use to describe it? That is where the next stage of this exploration begins. Before we miss life in the universe, we exclude it. Not deliberately, not out of ignorance, but through definition. Modern science relies on precise language, and precision always comes at a cost. To study life, we first had to decide what counts as life. Over time, those decisions hardened into criteria: carbon-based chemistry, liquid water, metabolism, reproduction, evolution through genetic inheritance. These requirements feel reasonable because they describe everything we know, but they also describe only one branch of possibility. The danger lies not in defining life, but in mistaking a working definition for a universal one. Biology as a discipline grew out of Earth's conditions. Its language was shaped by organisms that breathe, eat, grow, and divide on a sunlit surface. When we export that language to the cosmos, we quietly assume that the universe followed the same path. Physics offers no such guarantee. At a fundamental level, life is not a substance. It is a process, a system that maintains internal organization by exploiting external energy gradients while preserving information over time. Carbon and water are effective tools for this on Earth, but they are not mandated by physical law. They are contingency solutions that worked here. Once life is reframed this way, a gap opens between biological life and lifelike systems. A biological organism is localized. It has boundaries. It performs metabolism in a recognizable way. A lifelike system, in contrast, may be distributed. Its boundaries may be statistical rather than physical. Its metabolism may be a slow network of reactions spread across an environment. Its information may be encoded in structure rather than molecules we recognize. Under traditional definitions, such systems are invisible not because they do not exist, but because they fail to qualify. This creates what might be called the definition trap. We design instruments to detect oxygen because oxygen is a biological waste product on Earth. We search for liquid water because terrestrial life uses it as a solvent. We expect metabolism to leave clear chemical signatures because Earth's biosphere does so at scale. But each of these expectations filters reality through a narrow lens. Life that does not breathe oxygen leaves no oxygen. Life that does not metabolize rapidly leaves no obvious waste. Life that does not concentrate itself leaves no clear boundary. From our perspective, nothing is there. This is not a failure of observation. It is a failure of imagination constrained by history. The irony is that science already recognizes lifelike behavior outside biology. We study self-organizing systems. We analyze chemical networks that stabilize themselves. We model dissipative structures that persist by channeling energy flows. In physics and chemistry, these phenomena are treated as precursors, analogues, or curiosities, but rarely as candidates for life. The distinction is cultural, not physical. We reserve the word life for systems that resemble us, even when other systems meet the same functional criteria: organization, persistence, adaptation, memory. These properties appear in many contexts, but we draw a line around biology because that is where our intuition is strongest. The universe does not respect that line. If life elsewhere followed a different evolutionary route, one that never produced discrete organisms, rapid metabolism, or clear reproduction, our definitions would simply fail to catch it. We would observe the system, describe its behavior in physical terms, and move on. Invisible life does not announce itself as alive. It simply continues. This realization reframes the search for extraterrestrial life in an uncomfortable way. The problem may not be that life is rare. The problem may be that we have defined it so narrowly that only one outcome qualifies. The more unfamiliar life becomes, the less likely we are to recognize it as such. And this brings us to a deeper question. If life does not need to be an organism, and if it does not need to fit within biological categories, then what form could it take instead? To answer that, we must abandon the idea that life must be localized in bodies at all, and explore the possibility that life can exist as a distributed process spread across environments rather than confined within organisms. One of the strongest assumptions we carry about life is that it must have a body, something bounded, something you can point to, an organism that exists in one place at one time, separated from its surroundings by a clear boundary. Cells, tissues, shells, membranes. These structures feel so fundamental that it becomes difficult to imagine life without them. Yet boundaries are not a requirement imposed by physics. They're a solution that happen to work well on Earth. Bodies evolve because they concentrate processes, they make energy use efficient, they protect information, they allow rapid response to change. In environments where energy is abundant and conditions fluctuate quickly, localization is advantageous. But in quieter environments, concentration is not always optimal. Life does not need to be gathered in one place to persist. A distributed lifelike system would not exist as a single organism. It would exist as a network of interactions spread across an environment. No individual part would be alive on its own. Life would emerge from the relationships between parts, not from the parts themselves. Physics already provides examples of such behavior. Chemical reaction networks can sustain themselves across large regions without a central core. Certain pathways reinforce their own components, ensuring that the reactions which support them continue while others fade away. Information is not stored in a molecule, but in the structure of the network, the way reactions connect and feed back into one another. In these systems, there is no body to point at. Remove one region and the system continues elsewhere. Disturb part of the network and it reconstitutes itself from what remains. Identity is not tied to location but to pattern. Persistence replaces presence. Such life would be extraordinarily difficult to detect. There would be no organism to image, no population to count, no biomass to measure. The system would not cluster in a way that stands out. It would be smeared across its environment, embedded within ordinary physical processes. From a distance, it would look like chemistry behaving normally. This invisibility is not a flaw, it is an advantage. A distributed system is harder to eradicate than a localized one. It has no single point of failure. Radiation impacts or environmental shifts may damage parts of it, but the overall pattern survives. Over long timescales, this resilience becomes decisive. Evolution still operates in such systems, but it does so quietly. Variations appear as slight changes in reaction pathways or interaction strengths. Some configurations persist longer than others. Feedback loops reinforce what works and suppress what does not. Selection occurs not through competition between organisms, but through the survival of patterns. There is no birth, no death, only persistence and disappearance. From our perspective, this does not look like life. It looks like complex chemistry. But the distinction between the two may be artificial. If a system maintains itself by exploiting energy gradients, preserves information in its structure, and adapts over time to changing conditions, then it satisfies the core functional criteria of life. The absence of a body does not disqualify it. It merely makes it unfamiliar. This challenges one of our deepest intuitions. We tend to equate individuality with existence. If something cannot be isolated, counted, or captured, we struggle to treat it as real. But many of the most fundamental phenomena in physics fields, waves' collective behaviors exist without sharp boundaries. Their reality is not diminished by their lack of form. Life may be no different. If distributed lifelike systems are possible, then entire regions of space could host ongoing biological processes without ever producing organisms. Life would be happening, but nowhere in particular. It would be a property of the environment rather than an occupant of it. This possibility radically expands the scope of habitability. It suggests that life does not need planets, sunlight, organisms, or even clear beginnings and endings. It needs only conditions that allow organization to persist and patterns to reinforce themselves over time. And once we accept that, another assumption begins to unravel. If life does not require bodies, then it may not require metabolism in the way we understand it either. That realization leads directly to the next stage of this exploration. One where life operates so slowly, so subtly that it barely appears active at all. Metabolism feels like the heartbeat of life. On Earth, living systems are defined by constant activity. Molecules flow through cells. Energy is consumed and released. Growth, repair, and reproduction leave unmistakable signs of motion. Even when organisms rest, their chemistry never truly stops. From this perspective, a system without visible metabolism appears lifeless by definition. But this intuition is shaped by speed, not necessity. Metabolism is not a requirement imposed by physics. It is a strategy, a way of exploiting abundant energy in environments where change happens quickly. When energy is scarce, or when conditions remain stable for long periods, a different strategy becomes viable, one that minimizes activity rather than maximizing it. In such environments, life does not rush. Chemical systems can exist in states that are functionally dormant yet not dead. Reactions slow to a crawl. Energy flows weaken but do not vanish. Information remains encoded in structure waiting for conditions to shift. From an external viewpoint, nothing appears to be happening. Internally, persistence continues. Earth already offers examples of this principle. Certain organisms can suspend nearly all metabolic activity for extended periods. They survive freezing desiccation and radiation by entering states where chemical reactions slow to near zero. When energy becomes available again, activity resumes not from the beginning, but from a preserved configuration. Time passes, but the system remains intact. Now imagine environments where such dormancy is not a temporary response, but the default condition. In deep subsurface regions, within cold interiors or inside stable chemical networks, energy inputs may arrive only sporadically. Instead of continuous metabolism, systems operate in pulses. Brief activation is followed by long quiescence. Chemistry advances in steps rather than streams. Over millions of years, these steps accumulate. Evolution does not require constant motion. It requires that changes persist. If a system activates once every 1,000 years but retains information between activations, selection can still operate. Slow systems are not excluded from evolution. They simply evolve on timescales that challenge our perception. This creates a profound observational problem. Our instruments are designed to detect activity, heat, motion, chemical flux. We look for things that are happening now. Life that spends most of its existence inactive will evade every such search. It does not produce steady waste products. It does not alter its surroundings continuously. It leaves no trail of ongoing change. From our perspective, it blends into non-life. Yet from a physical standpoint, the distinction between an inactive living system and an inert one may be smaller than we assume. The difference lies not in activity but in potential. The capacity to resume organization when conditions allow. Life without continuous metabolism prioritizes memory over motion. Energy is not spent maintaining high throughput. It is conserved in structure. Damage accumulates slowly. Repair happens rarely but effectively. Systems are designed to last, not to grow. In environments where disruption is minimal, this strategy is not just viable, it is optimal. This idea forces a re-evaluation of what it means for a system to be alive at any given moment. If life operates on geological or cosmic timescales, then our snapshot observations are fundamentally inadequate. We may be mistaking slowness for absence, inactivity for death. The universe may host systems that are alive in the same way mountains are dynamic, changing imperceptibly yet never static. Such life would not advertise itself. It would not compete aggressively. It would not spread rapidly. It would not dominate its environment. It would persist quietly embedded within physical processes that appear ordinary because they change so slowly. Recognizing this possibility requires abandoning one of our strongest biases that life must look busy to be real. In the cosmic context, busyness may be a liability. Activity increases exposure. It accelerates decay. Systems that minimize motion minimize risk. Over billions of years, restraint can outperform exuberance. If life can exist without continuous metabolism, then another assumption begins to fail as well. We often expect life to reshape its environment, leaving clear biosignatures behind. But a system optimized for dormancy and persistence may do the opposite. It may avoid change entirely. That realization leads directly to the next challenge. What if the most successful life is the kind that leaves no trace at all? One of the strongest expectations in astrobiology is that life announces itself by changing its environment. On Earth, this assumption works. Oxygen floods the atmosphere, methane fluctuates, landscapes are reshaped. Even from orbit biology leaves fingerprints that stand out against purely geological processes. It feels natural to conclude that if life exists elsewhere, it should do something similar. But this expectation confuses visibility with success. Changing an environment is not a requirement for life. It is a side effect of abundance. When energy is plentiful and competition-intense organisms expand, they consume resources faster than equilibrium can restore them. Waste accumulates. The environment shifts. Biosignatures emerge. Remove abundance and the strategy reverses. In environments where energy arrives slowly and conditions remain stable, altering the surroundings is risky. Any significant change threatens the gradients that sustain the system. In such settings, the most successful life is not transformative but conservative. It survives by interfering as little as possible. This form of life would be nearly invisible by design. Its processes would be tightly coupled to existing physical and chemical cycles. It would recycle products efficiently, leaving minimal waste. Its energy use would remain below the threshold that produces detectable heat or chemical imbalance. From the outside, everything would appear to be functioning exactly as physics predicts. And that is the point. A system that blends perfectly into its environment is harder to disrupt. It does not trigger feedback loops that attract attention. It does not destabilize the conditions it depends on. Over long timescales, this restraint becomes a powerful evolutionary advantage. Earth already hints at this possibility. Much of the planet's microbial life operates at low energy levels, recycling materials locally without altering global conditions. Entire communities exist that leave no obvious biosignatures at planetary scale. If Earth were observed from afar during much of its history, these forms of life would be undetectable. Now extend that logic beyond Earth. Imagine life emerging in subsurface regions inside cold interiors or within distributed chemical networks. There is no incentive to modify atmospheres or surfaces. In fact, doing so would be counterproductive. Stability is preserved by maintaining equilibrium, not by breaking it. Such life would leave no oxygen spike, no methane haze, no thermal anomaly, no surface alteration. It would not even create a biologically active environment in the traditional sense. It would simply exist within physical processes, exploiting them gently and persistently. From our perspective, nothing is wrong. This creates a paradox. The more successful this kind of life becomes, the harder it is to detect. Its survival depends on invisibility. Any detectable signal is by definition a failure of optimization, a leak in an otherwise efficient system. If this model is correct, then many of the worlds we label as sterile may be anything but. They may host life that has perfected the art of non-interference. This forces a reconsideration of biosignatures themselves. Instead of looking for strong signals, we may need to look for their absence places where chemistry remains delicately balanced for far longer than expected. Environments that refuse to drift toward equilibrium despite having ample time to do so. Systems that look too stable to be entirely lifeless. These are subtle clues, not definitive proofs. They demand patient statistical comparison and a willingness to accept ambiguity. They also demand humility. We must accept that life does not owe us evidence. It does not need to advertise its presence to be real. If anything, the universe may reward the opposite behavior, Life that survives for billions of years may do so precisely because it avoids being noticed. It becomes a quiet passenger in its environment, indistinguishable from non-life except in the persistence of its organization. And once this possibility is acknowledged, another uncomfortable realization follows. Perhaps life is not hidden because it is rare. Perhaps it is hidden because it is good at surviving. That realization pushes us toward an even deeper boundary. One where the distinction between life and non-life becomes increasingly blurred. Not because life disappears, but because it merges seamlessly with the physics that sustains it. That boundary is where we must go next. There is a point where the distinction between life and non-life begins to lose its clarity. Not because life becomes rare, but because it becomes subtle. At that boundary, organized systems persist, adapt, and resist decay, yet they do so using the same rules that govern ordinary physical processes. No membranes, no cells, no obvious metabolism, just structure, feedback, and time. Physics already describes many such systems. We study self-organizing patterns in fluids. We model chemical oscillations that maintain themselves far from equilibrium. We observe structures that emerge spontaneously in plasma's magnetic fields and reaction networks persisting longer than chance would allow. These systems are treated as natural phenomena, not biological ones, because they lack familiar markers. But familiarity is not a criterion of reality. At their core, these systems exhibit behaviors that mirror the functional essence of life. They draw energy from gradients. They maintain internal order. They respond to disturbance. Some even display forms of memory returning to previous configurations when conditions repeat. In every operational sense, they behave like living systems, except that they do not resemble organisms. This is where invisibility becomes inevitable. If life expresses itself as an extension of physical law rather than a violation of it, then it will not stand out. It will not announce itself with anomalies that break our models. It will appear as physics working normally, perhaps too normally. The only difference will be persistence organization that endures longer than expected without drifting into equilibrium. From the outside, this does not look alive. It looks boring. And that may be the greatest camouflage of all. Our scientific instincts are trained to notice deviations. We search for things that do not fit. But life that hides within physical law produces no sharp edges. It doesn't challenge equations. It fulfills them. It exists precisely because it obeys the rules so well. In such a universe, the most advanced forms of life may not sit above physics, but within it. This possibility reframes the question of alien life in a radical way. Instead of asking whether life exists somewhere, we must ask whether we are prepared to recognize life that does not distinguish itself from its environment, life that is not an occupant of the universe but a mode of behavior within it. If such systems exist, they would never be catalogued as biological. They would be classified as chemical phenomena, plasma dynamics, or emergent structures. Their persistence would be attributed to stability. Their adaptation would be labelled feedback. Their memory would be described as hysteresis or path dependence. Life, in other words, would be renamed. This does not mean that biology is an illusion. It means that biology may be a special case, a highly concentrated, high-energy expression of a broader category of organised systems. On Earth, life became visible because the environment favoured speed, abundance, and expansion. Elsewhere, different conditions may favour subtlety, integration, and endurance. In these settings, life does not rise above physics. It dissolves into it, and that dissolution has a profound consequence for detection. If life is not something that breaks physical expectations, then searching for anomalies may never reveal it. We may need to search instead for systems that are too stable, too persistent, or too finely balanced to be explained easily. But even that distinction is fragile. At some point, explanation and recognition merge. This leads to a deeply unsettling idea. Perhaps life is not hidden behind exotic chemistry or unfamiliar environments. Perhaps it is hidden because it does not look like a separate category at all. It looks like the universe doing what it always does, organizing itself wherever energy flows allow. If that is true, then the boundary between life and non-life is not a wall. It is a gradient, and we are standing somewhere in the middle, mistaking one side for the whole. That realization does not end the search for life. It changes its meaning, and it prepares us for the final challenge of this exploration, one that does not concern where life exists or how it functions, but whether the human mind is capable of recognizing life that does not confirm its expectations. That challenge lies in time itself. There is another way life can disappear from view without hiding at all. It can move too slowly. Human observation is tuned to short timescales. We notice change that happens over seconds, days, or years. Even in astronomy, where patience is required, our measurements still capture moment snapshots, compared against models that assume relatively rapid evolution. Anything that unfolds more slowly than our window of attention fades into the background. Life does not have to respect our sense of time. If energy flows are weak but stable, and if environments remain undisturbed for long periods, organization can proceed at a pace that is almost geological. Reactions advance incrementally. Structures adjust gradually. Information accumulates so slowly that no single moment reveals meaningful activity. Life is present, but it is never doing anything obvious. From our perspective, it looks inert. Earth offers hints of this phenomenon. Geological processes driven by biology, such as long-term mineral alteration, often unfold so slowly that their living contribution is invisible without careful reconstruction. Microbial ecosystems can persist with turnover times measured in centuries or longer. In extreme environments, biological clocks slow dramatically, yet persistence remains. Now imagine systems where this slowness is not an exception but the norm. In dark energy-limited environments, rapid change is dangerous. Fast reactions risk destabilizing the gradients that sustain the system. Selection favors processes that advance cautiously, conserving structure and information over immense spans of time. Life becomes a long-term project rather than an active one. Such systems would never register as alive in real-time observation. A telescope might observe a region for decades and detect no meaningful variation. Spectra remain constant. Temperatures hold steady. Chemical ratios drift only within expected margins. Every test confirms lifelessness because every test assumes that life, if present, would move faster. This is temporal invisibility. Life exists, but its tempo falls outside our detection bandwidth. It does not pulse, flare, or fluctuate. It advances in increments too small to register against background noise. To see it, one would need observations spanning millions of years compared not to static models but to evolving baselines. This requirement alone may exclude us. Human science is powerful, but it is short-lived. Instruments are upgraded, missions end, data sets fragment, continuity is rare. A form of life that requires uninterrupted observation across geological timescales is effectively invisible to any single civilization, and yet such life could be widespread. Slow life has advantages that fast life lacks. It is resilient to disruption. It survives impacts, radiation, and environmental shifts simply by not reacting strongly to them. It doesn't overshoot. It does not collapse dramatically. Over time, it outlasts more energetic systems. In the universe, endurance may matter more than speed. If life commonly adopts this strategy, then the cosmos could be filled with living systems that appear unchanged across epochs. They would not announce beginnings or endings. They would simply persist, adjusting infinitesimally as conditions drift. This reframes another core assumption. We often imagine life as something that emerges, flourishes, and evolves visibly. But life that unfolds too slowly does not fit this narrative. It doesn't produce milestones. It produces continuity. Its success is measured not in expansion or complexity, but in survival. Detecting such life would require a different mindset. Instead of asking what's changing now, we would need to ask what has refused to change over impossibly long periods. Stability, not activity, becomes the clue. Persistence, not motion, becomes the signal. But even this approach is uncertain. Physical systems can also remain stable for long times without life. Distinguishing between lifeless persistence and living persistence becomes nearly impossible when timescales exceed observation. The difference may lie only in history and paths taken rather than states observed. And that leads to a final uncomfortable realization. Life that moves too slowly does not just evade our instruments. It challenges the very notion that life must be detectable within a single observer's lifetime. If the universe hosts such systems, then life may be everywhere and nowhere at once, present, enduring, and functionally invisible to any species that looks for answers too quickly. With that realization, the final obstacle comes into focus. Even if we accept invisible life, distributed life, slow life, and physics-like life, we're left with one last question. What happens when every signal life produces blends perfectly into noise? That is the collapse we must face next. At some point, invisibility becomes indistinguishable from absence, not because nothing is there, but because every signal blends perfectly into what we already expect to see. Physics predicts variability. Chemistry produces complexity. Noise exists everywhere. When life operates quietly enough, its presence no longer stands apart from these backgrounds. It collapses into them. This is the most difficult barrier in the search for alien life. Detection relies on contrast. A signal must rise above expectation. It must violate a baseline challenge, a model, or create an imbalance that demands explanation. Oxygen in a reducing atmosphere, heat where none should exist, motion that resists decay. These are the clues we know how to follow. Invisible life produces none of them. A lifelike system optimized for stability will generate signals that fall comfortably within physical predictions. Its energy use will be low. Its chemistry will recycle efficiently. Its structures will align with forces already at work. Every observation will have a non-biological explanation that fits neatly within existing theory. And that explanation will usually be correct. This creates a paradox. The more compatible life is with its environment, the less detectable it becomes. Systems that push their surroundings far from equilibrium are easier to notice, but also easier to disrupt. Systems that remain close to equilibrium persist longer but vanish into noise. From the perspective of science, noise is not mysterious. It is expected. Measurements always contain uncertainty. Models always allow margins. Life that operates within those margins does not stand out. It does not trigger alarms or inspire headlines. It is catalogued, averaged, and explained away. This is not a failure of rigor. It is a consequence of method. Science is designed to minimize false positives. Faced with ambiguity, it favors conservative explanations. A chemical anomaly becomes geology. A thermal variation becomes instrumentation. A pattern becomes coincidence. These choices are rational, but they also bias discovery against subtle phenomena. Invisible life exploits this bias without intent. Its signals are not sharp spikes, but long, shallow curves. Not deviations, but correlations. Not events, but histories. To recognize such life, one would need to detect patterns across many systems, not anomalies within one. Persistence across environments becomes more important than magnitude within any single case. This is a fundamentally different kind of evidence. It requires comparison rather than detection, statistics rather than signatures, theory-driven expectation rather than surprise. Instead of asking what is unusual here, we must ask what's consistently too ordinary across many places. Even then, certainty remains elusive. A universe governed by physical law naturally produces recurring patterns. Distinguishing between law-driven repetition and life-driven persistence may be impossible in principle. The two may be inseparable at sufficient subtlety. This raises an uncomfortable possibility. Perhaps there is no observational boundary where invisible life suddenly becomes detectable. Perhaps beyond a certain point, life and non-life are observationally equivalent, not because life disappears, but because its behavior converges with the behavior of stable physical systems. If that is true, then the question of detection gives way to a question of interpretation. We may never be able to say with confidence that a given system is alive. We may only be able to say that it behaves in ways consistent with long-term organization under weak energy flow. Whether that organization deserves the label life becomes a philosophical choice rather than an empirical one. And yet, this does not render the search meaningless. It reframes it. Instead of seeking proof, we seek plausibility. Instead of certainty, we accept probability. Instead of sharp answers, we build frameworks that allow lifelike behavior to exist without demanding that it reveal itself. This is not a retreat from science. It is an expansion of it. Recognizing the limits of detection does not close the question of life in the universe. It opens it in a more honest way. It acknowledges that some forms of life may be real, persistent, and utterly beyond our capacity to confirm. The universe does not promise that everything important can be observed. And if life is among those things, then our relationship with the cosmos changes. We stop asking whether life is out there in a way we can see. We start asking whether the universe is capable of supporting organization so subtle that seeing it was never the point. That realization brings us to the final synthesis of this exploration. Not a conclusion about where life exists, but about what it means to recognize life at all. Once invisibility is taken seriously, the universe begins to look very different. The familiar picture of a mostly empty cosmos dotted with rare, isolated biospheres starts to dissolve. In its place emerges a quieter possibility. A universe rich in organization but poor in spectacle. Life does not cluster around bright stars or announce itself through dramatic transformations. It spreads thinly, embeds deeply, and persists without fanfare. In this universe, life is not exceptional. It is restrained. Everywhere that energy flows gently and consistently, systems have the opportunity to organize. Not explosively, not in ways that reshape their surroundings, but in ways that endure. These systems do not compete for dominance. They coexist with their environments tuned so precisely that they become almost indistinguishable from the physics that sustains them. Such life would not resemble ecosystems as we imagine them. There would be no forests or oceans visible from afar, no atmospheric revolutions, no planetary scale signatures. Instead, there would be countless pockets of quiet organization, chemical networks here, slow adaptive processes there, each exploiting local gradients just enough to persist. From the outside, these regions would appear unremarkable. This idea reframes one of the most troubling questions in science. The apparent silence of the universe has often been taken as evidence against widespread life. If the cosmos were alive, we reason we should see signs of it, but that reasoning assumes that life seeks visibility, that it expands outward, that it leaves scars on its environment. Those assumptions may reflect our own evolutionary history more than any universal principle. Silence may not indicate absence. It may indicate success. Life that remains quiet avoids competition. It avoids disruption. It avoids detection. Over billions of years, these advantages accumulate. Loud life burns fast. Quiet life persists. In a universe measured in deep time, persistence matters more than expression. This perspective also reshapes how we think about complexity. We often equate life with increasing complexity, assuming that evolution naturally drives systems toward greater structure and activity. But complexity is costly. It requires energy maintenance and constant repair. In environments where energy is limited and stability is high, simpler, more integrated systems may be favored indefinitely. A universe filled with quiet life would not be marching toward intelligence or technology. It would be settling into durable patterns that resist decay. This does not mean that intelligence or technological civilizations are impossible. It means they may be rare, fragile outliers, brief flares in a cosmos otherwise dominated by long-lived, low-profile forms of organization. From this viewpoint, humanity's own visibility becomes unusual. Our signals are loud, our energy use is intense, our impact on our environment is unmistakable. These traits make us easy to notice, but they may also make us temporary. In contrast, invisible life pays no such price. It survives by not standing out. The universe then may not be empty of life. It may be saturated with it, just not in ways that align with our expectations. If this is true, the search for life becomes less about discovery and more about humility. We are not explorers looking for rare treasures in a barren expanse. We are newcomers learning to recognize forms of organization that do not announce themselves and that may have been present long before we arrived. This realization does not answer the question of whether we are alone. It dissolves the question itself. Aloneness implies separation. It implies that life is something that exists in discrete countable units. But a universe filled with quiet life is not one where beings are isolated. It is one where organization is continuous, varied, and deeply embedded in physical reality. We may not be alone. We may simply be one of the few forms of life that insists on being seen. And that brings us to the final step of this exploration, not a search for more examples, but a reckoning with what recognition itself requires. Because in a universe like this, the hardest question is no longer where life exists. It is whether the human mind is capable of recognizing life that does not resemble itself. At the end of this exploration, the problem no longer belongs to the universe. It belongs to us. We began by asking where alien life might exist, then how it could survive without planets, without sunlight, without familiar chemistry. But step by step, those questions gave way to a deeper realization. The greatest barrier to finding life may not be distance, rarity, or technology. It may be recognition itself. Human understanding is shaped by contrast. We recognize things by how sharply they stand out. Motion against stillness, heat against cold, structure against randomness. Life on Earth fits this pattern because it evolved in an environment that rewards visibility. It grows quickly, spreads aggressively, and reshapes its surroundings. It demands attention, but nothing in physics requires life to behave this way. If life emerges in environments where stability is more valuable than expansion, then subtlety becomes adaptive. Organization blends into background processes. Persistence replaces growth. In such cases, life does not appear as an exception to physical law, but as one of its quiet outcomes. From the outside, nothing seems different. This is the uncomfortable conclusion of the series. The universe may not hide life behind distance or obscurity. It may hide it behind familiarity. Life may look exactly like what we already call physics, chemistry, or noise, because it operates using the same rules at the same scales and within the same expectations. At that point, the distinction between life and non-life becomes less about observation and more about interpretation. What does it mean to recognize life? Is it metabolism or persistence? Is it reproduction or memory? Is it change or the refusal to change? Each definition reveals some forms of life and conceals others. None are neutral. Every definition is a filter shaped by history, perception, and human experience. This does not imply that life is unknowable. It implies that life may not be a category waiting to be discovered, but a spectrum waiting to be understood. Biology, in this view, is not a separate domain carved out from physics. It is a region within it, a place where energy, information, and time intersect in ways that sustain organization. Earth sits in one such region. Other regions may look nothing like it. If life elsewhere is quiet, slow distributed, or deeply embedded in physical processes, then no single observation will ever confirm its presence. There will be no moment of discovery, no unmistakable signal, no definitive proof. There will only be increasing plausibility frameworks that allow lifelike behavior to exist without contradiction. This challenges a deeply held expectation. We often imagine that discovering life elsewhere would be a dramatic event, a signal detected, a biosignature confirmed, a boundary crossed. But in a universe filled with quiet life, discovery may instead be a gradual shift in understanding, a realization that the universe has been doing something subtle all along. In that sense, the search for life is not only an outward journey, it is an inward one. It asks whether we can loosen our attachment to familiar forms, whether we can accept that life may not resemble organisms, ecosystems, or civilizations, whether we can recognize organization that does not announce itself, intelligence that does not communicate, and survival that does not expand. The universe does not promise to be legible to us. It does not promise that the most important processes will be obvious, dramatic, or accessible within a single lifetime. It offers patterns, persistence, and possibility, and leaves interpretation to those who observe. If life exists everywhere but appears nowhere, that does not make it meaningless. It makes it profound. It suggests that the universe may be alive in a way that transcends categories, quietly organizing itself wherever energy flows allow, and that we, rather than standing apart from that process, are one expression of it, loud, brief, and intensely visible. Whether we are capable of recognizing quieter expressions remains an open question, and that question does not end this series. It opens the door to everything that follows.